Hi, my name is Hugh Holbrook. I am the Chief Development Officer at Arista. My background is software. I'm involved in many things like designs with cloud customers, partnering with the hardware team, partnering with customers on their next generation designs. Today I want to talk about AI networking, challenges of AI networking, things we can do to make AI networks better, and then I'm going to walk you through some AI network designs that we're seeing some of our customers at all scales deploy. So this here is a picture that is probably familiar to you now. This was actually shown by Alexis Bjorlin at Meta at OCP. This is 2 years ago, and it almost doesn't matter. Like, this is showing the size of AI models and the compute. It almost doesn't matter what the axes are or what actually is on the y-axis, but it's a very clear up and to the right graph. And the statement that the AI networking is growing faster than the data center network in many cases used to be a shocking statement. Now it's more of a duh moment. Like, yes, we've all heard about it. It's been nonstop. Today, OpenAI announced a new O1 model. I mean, models continue to get bigger and larger. The larger models use more GPUs, and they result in larger networks. So this is part of the challenge of AI networks. AI networks, fundamentally, are running both inference and training. When they're training, they're running large neural networks. So very, very large neural networks, many copies of large neural networks. The picture of a tiny little part of a neural network. Every one of those arcs has a weight associated with it, and the training of a neural net figures out the values of those weights and is extremely computationally intensive. There are billions, hundreds of billions, even trillions in the latest models of weights to tune in the largest models. It's very, very computationally intensive. So much so that it can't be done on a single GPU, which is why we have clusters of tens of thousands of GPUs that train, and tens of GPUs or more to do inference on these models. Training and inference is computationally intensive, especially training, which is what's pushing the demands on the network. This is a picture of a server. This is an OCP design that Meta has built. On the right, servers like this that are used for AI training are the most demanding citizens on the network that anybody's ever seen. They saturate the links with wire rate traffic, which tends to be bursty. There are very few flows coming out of a server compared to like a server in a hyperscale cloud. I might have a VM, which is kind of a mean server with a lot of capacity, but there'll be thousands or tens of thousands of flows on it. An AI server in the middle of training might have 4 flows coming out of it, or 8 flows, which is very challenging for the network. The traffic tends to be synchronized because there are distributed algorithms running that perform this training. So all of the servers are bursting at wire rate simultaneously. Again, you can imagine the demands on the network. And then, lastly, on top of it, the nature of these distributed computations is such that the slowest flow matters. So as opposed to, a server farm serving storage requests or serving, web requests, once in a while, if my web request takes a little bit of time, I don't really notice it. But one slow flow can slow down thousands of GPUs. And if there's enough GPUs running in a distributed computation, there's always one that's slow, unless you're careful. And so you're always running slower. So these are the problems of AI networking that we have set out to address, and that I'm going to talk about. I want to talk a little bit about Ethernet. Ethernet, we're just seeing tremendous traction, and it's kind of a foregone conclusion, I think, that Ethernet, from my standpoint, will be dominant in AI networking going forward. It has compelling advantages for our customers. It's all the things that it's a deep multi-vendor ecosystem of switches, NICs, optics, PHYs, tooling. It's well understood. Everybody learns about it. There's lots of training. There's lots of books. There's lots of availability. It's well understood technology. There's no limit on scaling. It's proven to scale to the entire internet scale, Ethernet and IP. And there's just a consistent track record of innovation in advancing from 1 gig to 10 gig to 25 gig to 40 gig to 100 gig. Just 400 gig, 800 gig, 1.6T, just like very good innovation across the speeds, across all the layers. Just all of these advantages are compelling, and the advantages are larger in bigger scale networks. Like the bigger the network, the more this stuff matters. The bigger the network that you're running, the more complicated it is. So this is something that I wanted to address. I want to first talk about load balancing. Load balancing is probably, if I asked our customers what the biggest problem in AI networks are today, problems 1, 2, 3 is load balancing, load balancing, and load balancing. And I'll talk about why. So here's a super simple diagram of a two-tier network that shows, XPUs on the left trying to talk to 2 XPUs on the left trying to talk to 1 XPU on the right. On the left in this picture is kind of the bad version of things, where they're trying to get traffic to the same destination. They both pick the same spine. And so the congestion happens on the downlink from the spine to the destination. What I wanted to have happen was the 2 XPUs to pick different spine switches to reach the same destination, and then there's no congestion on the downlink from the spine. This is fundamentally the load balancing problem. Now, of course, scale this out to 32, 128 uplinks, 4 flows on every port, they're all going wire rate. I am saturating all of my uplinks because of the nature of the traffic simultaneously. So I don't have any extra capacity. I need to perfectly load balance 4 flows from downlinks. Every single uplink has to have exactly 4 flows on it. And so traditional load balancing algorithms just don't work that well. So that's kind of fundamentally the load balancing problem and why it's important. So we have multiple solutions for better load balancing. Kind of the state of the art before we started thinking about it was just ECMP, in which a top of rack switch, a tier 0 switch, just kind of effectively randomly maps one of those flows to an uplink. But that is a statistical balls in bins problem, and I get some links that have more and some links that have less, and that's not what I want. I want an even distribution. So we have multiple solutions that we've been working on. One is kind of congestion-aware placement of flows, or flowlets, which is kind of like active flows. And this is something we can do in which we decide which uplink to place a flow on based on the load. And that gets you very even distribution northbound out of a tier 0 switch. But it's fundamentally a greedy local algorithm and doesn't really solve the problem southbound out of, but it is better, and it is a meaningful improvement. And for networks where the workloads are, where there is some headroom, where there's some east-west traffic within rack, this actually works very well, and we have customers deploying this. Another technology that we've invested in is RDMA-aware load balancing, or cluster load balancing, in which we ensure through software algorithms that the traffic to any destination is using all of the paths equally. And this is software getting involved in figuring out how to load balance the flows, understanding the nature of the RDMA traffic. All of this training traffic fundamentally is IP, but the protocol over it is RDMA, not TCP. It's IP with UDP on top of that, and then RDMA on top of that. And so this works very well. We're seeing very good results in large networks. We have more enhancements on the roadmap. I'd love to talk about this, but I want to move on. But really solving this is a super important problem that we're very active on, and we have really good results with so far. There's a second solution, which is just a kind of a different network implementation, which is the distributed Etherlink switch. This in this solution, or the distributed scheduled fabric, we've talked about it, but the distributed Etherlink switch, this really solves the load balancing problem by taking out of a tier 0 top of rack switch any packet and sending it to all destinations in hardware. And this is a really nice architectural solution because it just avoids the load balancing problem because the hardware is spraying the packets. Now the packets are getting sprayed across all of the uplinks, and this requires the destination top of rack switch to put the packets back in order so that the end station doesn't see packets arriving back in order and doesn't impact the application. And this is all done in the tier 0 switch on ingress and on egress.
So you,
yeah.
Prefaces, non-networking experts. So when I think of something like packet spraying, it seems like you're going to be keeping all the paths more busy rather than less busy?
Well, I mean, I'm sending 1/nth of each flow on each of the paths. So like the total amount of traffic doesn't change, but instead of having a balls in bins problem where I've got kind of, a Gaussian curve of some links are really highly utilized and then others are underutilized, all of the links are evenly utilized. And so I can raise the total network utilization to 100% because I have enough capacity. Like northbound, like in these networks, the northbound capacity out of tier 0 is almost always equal or slightly greater than the southbound capacity toward the GPUs, but it's just a question of getting it evenly distributed. And that's the problem this solves.
What's going on is that you're choosing a path for an individual packet rather than choosing a path for the entire flow.
Exactly.
And so you're load balancing at the packet level, not at the flow level.
Exactly.
It's even better than that. It's not choosing a path. It's saying, if I've got 8 bytes, I'm putting 1 byte on every link. It's not choosing. It's just basically peanut buttering it across all available links.
That's right. It even goes below packets.
Right. So
we actually break
frame
cells.
Right.
And the cells get
think
spread.
of it as just like a SerDes, right? It's serializing to serializing. In this case, it's parallel to serial to parallel. You take your bits, you throw it across as many links as you can, push it down to the next layer, and move on to the next flow.
Yeah, so there's a cellularization. It's not quite at that level of granularity, but that's the idea, is that we like spray it across. And like the packets are very large, right? So there's like 8K packets or 4K packets in AI workloads. There's plenty of room to break it into smaller packets and evenly distributed.
And if you actually are paying attention to priority flow control, you can avoid paths that might be potentially blocked.
Right, and actually, so like, I mean, in this architecture, if I'm spraying evenly, like the links from leaf to spine and spine to leaf, they don't get congested because I'm evenly load balancing all of them. And there are mechanisms in the hardware to detect in hardware actually failed links, and so like detect the reachability of any destination. And so it does a very nice job of working around transceiver failures between tier 0 and tier 1, for instance.
And that works as long as you know what all the workloads are using that network. If there's only one workload. Yeah.
Well, so the nice thing about this is like this architecture is turns out to be very agnostic to the workload or even the transport protocol running on the end stations. So like any NIC running almost any transport protocol, like if there's not fan-in, like the network will deliver it. I mean, if there's fan-in, there's nothing I can do. If I have 800 gig going into 400 gig port, there's nothing I can do. But as long as like the workloads are evenly balanced, which AI workloads are, this will deliver the traffic without slowing it down in the network, which is exactly what you want. So tons of neat work in this, but like I don't have time to like go into details, the more details about it. That's another talk. The third solution that I think is kind of more on the horizon is a packet spraying transport protocol. So if in the future, I expect that we will see transport protocols like alternatives to RDMA or variants of RDMA that can deal with packets arriving out of order. And then I can spray packets. And spraying is actually the easy part. The hard part is taking packets that, as a result of spraying, arrive out of order and delivering them to the application without impacting the application. So AI traffic tends to be fairly accepting of this, or fairly, there are ways that I can tag the packets exactly with where they're going in memory and just directly place them in memory. This will require end station support. This is part of the solution of the Ultra Ethernet Consortium, which I'll talk more about. Ultra Ethernet Consortium NICs are on the horizon. In the near future, it's RDMA, but we support this, and I expect more deployments of this coming in the next year, 2 years. This is still pretty early days for this kind of technology. So that's probably the main problem that we're spending a lot of focus on in EOS on features. The other features in support of AI, I'll just walk through them really quickly. Like these are sort of problems, if load balancing is problem number 1, these are sort of problems 2 through 10, which are also important. The probably next most important problem is visibility. And my colleague Tom is going to talk about this in a follow-on here. But AI traffic is really hard to monitor, to get good performance out of, because it's very fast. Things happen on very short time scales. The problems are distributed. The workload's not always known. And like problems in the network don't necessarily manifest as a packet got dropped. It's just things run slower. Like, why did it run slower? Well, maybe it ran slower because it's the NIC, maybe it's the PCI, maybe it's the GPU is going into thermal slowdown, maybe it's the network, and you want to understand all of this. So it's like visibility. We have a whole suite of tools for visibility, and Tom is going to show you a very neat one later, which is extracting some information out of the end station that we can visualize that they give us really, really kind of deep insights on what's going on in the network and being able to correlate network with end station behavior. Support for congestion control is very important. Congestion control, if there is congestion, if there's fan-in on the last hop, how do we slow down? How do we not drop packets, not send packets faster than any given link can tolerate? Most networks that are running AI networks have priority flow control, PFC, somewhere in their network. If nowhere else, then just to make sure that like the last hop, like the host, there can be congestion within the host on the PCI bus, and just to push back to the network. It's funny, but like actually the network has bigger buffers than the NIC in a lot of cases, and so it's better to buffer it in the network than to buffer it on the NIC if there's congestion on the PCI bus, which actually can happen based on other competing workloads on the host, CPU slowdown, et cetera. ECN marking is typically required. We have like a long history of ECN marking. This is just marking packets when they go through a queue that's congested. And then there's other flavors that we support that are coming, which is like in various types of in-network telemetry, which is just finer grained information about congestion, queue depth in the network. And we have support for in-network telemetry. This is kind of, again, budding new work that I think is going to have a bigger impact in the future in conjunction with Ultra Ethernet NICs and in conjunction with future flavors of RDMA. Congestion control is super important, but like let me say, it's not an alternative to good load balancing. Like I can't solve a load balancing problem with congestion control. Like ideally, I would never need congestion control because nothing could possibly slow down because everything would be running at wire rate. All my traffic is evenly distributed across all the links. But there are places where I can't avoid needing congestion control, algorithms that produce fan-in into one host just by the nature of it, congestion on the PCI bus, et cetera. One feature that we support in EOS that's important, really important for some of our AI customers is the ability to like upgrade. There is no good time to bring down a switch in a lot of these cases. In a lot of cases, the network team is separate from the team that's the application team, and almost always the network team is separate from the application team that's running the applications. The network team sees the traffic, but they don't really know when a training job is starting, when a checkpoint is starting. And this is really true and kind of obvious at sort of a cloud service provider, but also true even with like just an in-house network. Like oftentimes the network team of a single enterprise treats their internal customers kind of the same way a cloud service provider does. Like, well, you get these GPUs, do what you want with them for the next month, and call me when you're done. So SSU is technology that we have that at tier 0 can upgrade from one release of EOS to the next release without taking any downtime. So packets continue to flow. We're happy to keep it's sort of changing the tires on the car while it's driving down the freeway, right? So, this is a really valuable technology that really aids the operation of these AI networks for customers that need to upgrade for new functionality or for bug fixes, et cetera, and they can do this without impacting their application customers.
Now, is that upgrade done in a cascade, or do they all have to be flipped at the same time?
I think usually they do it in a cascade, but we've done this technology is like well trodden for us. We have customers that have done tens of thousands.
One of your first demos you did when you started off
Right.
is just to show your traffic. Oh, look, we did an upgrade. Who can find the upgrade?
Yeah, no, it's very neat technology that we've been supporting for a long time.
Yeah.
And so the idea is they don't have to cascade, although customers are cautious. But it doesn't impact the traffic, so it doesn't really matter if you cascade or not.
But one of the challenges customers have is managing the switches. So they don't want to trigger necessarily a firmware upgrade themselves. They want to use a tool to do that.
Right.
You have tools around that?
We do, and this is really, this is a whole nother kind of like deeper conversation, but CloudVision is our system for managing a fleet of switches, tier 0, tier 1 switches, for detecting
Their switches.
for our switches, Arista switches, for detecting, compliance, what bugs you're exposed to based on the configuration that you're running actually in the network, for triggering updates, for rolling updates. So this is a system, we have customers that are using Cloud Vision for AI networks. Some of the very largest customers, they build their own systems to manage it. And we're trying to give them that sort of visibility and upgrade manageability and on the whole network through that tool. We have a lot of work on data plane tuning. And it's like, this is a, dare I say, black art to just like get the most out of the silicon. We have a long storied history on this. I won't go into the details, but there's a lot of work to do. And the Arista switches actually are field hardened here, and we've learned a lot from our deployments already. That goes into every one of our customers that deploys an Arista AI.
So Hugh, you mentioned that some of the largest customers do their own management solution. I mean, are you API driven at that level?
Yes.
I mean, you're providing the telemetry, like open telemetry, or
exactly. So we do open config streaming where there are open config models that they want. We also have sort of GNMI based streaming of the telemetry data running on a switch that gives them visibility of every single piece of state that we monitor in a switch. And that's really valuable for the cloud customers, like specifically are building their own systems, because they look at it and they're like, one thing we do really well is ingest a lot of data, analyze it, and make decisions based on that. Like that is their bread and butter, right? And so like they're really happy with our ability to export them a ton of state about interface state, thermals, route changes, link up, down, etc. Oops, I'm going the wrong way. But like all of these features are cool, but the most important feature, if there is one, is the things listed on this slide, just the basics of fast, reliable route convergence and link down handling, solid L1 link monitoring. Like some of these networks might have 400,000 transceivers in them, right? Like, I mean, it's just like a tremendous amount of devices that can fail, be flaky, have intermittent behavior. Time to market is super important. There's a lot of urgency when GPUs show up to deploy the network and not have the network be a bottleneck. And there's a lot of urgency on getting to the next generation silicon, because the next generation silicon is so much better. It's better in terms of power, in terms of cost, in terms of scale. So customers want the next generation silicon. All this has to be done, but if there's one thing that really matters, it's quality. Like they cannot afford downtime in these networks. It has to work. It has to work reliably once it's deployed in very demanding situations. So like if there's one thing that we focus on, it's quality above all else. And it's super important for these deployments. So
what was DOM in that?
It's digital optics monitoring. So it's like deep data on transceiver monitoring. It's sort of
There's so many things can go wrong.
Various
Optical
standards.
transceiver, you just gotta keep track. And how many? What's a typical number of optical transceivers in a large scale build?
Oh well, I mean it's like 4 times the number of GPUs in a lot of cases, right? So if I have 100,000 GPUs, which is a pretty large network, if I have 100,000 GPUs, there's 400,000 optics. I'm just like, there's always one that's going down.
Each one of those represents something that could go wrong and will go wrong.
And like every day, something is failed and it matters, and so they want to monitor that, understand it, pull things out before they fail, proactively.
And predict. Yeah, exactly. Yeah.
Exactly. And there's telemetry data that we can export that helps with that. Oops, going backwards. So I want to just talk about, I'm not really going to talk much about this. Harddev talked about this. Basically, all of our next generation designs are based on these platforms, either based on a couple different emerging silicon and systems based on it, or the DES silicon. So here's like a network like that we have deployed today, relatively small scale. It's just plug your GPUs into a 7800. This is actually like not tiny scale, and this is not an inexpensive network to deploy. If you have 576, 400 or 800 gig GPUs, like this is like a significant deployment. We get really great performance. We have this deployed for both inference and training. The limit is it just scales to 576, 800 or 1152, 400 gig ports. Here's a much larger scale network that we have also have customers doing. A 3-tier network. This is based on 7060 switches. This can scale out to north of 50,000 GPUs in a network that looks like this, based on 51T leaves. The leaves can be in the same rack. That's pretty dense. They could be kind of a middle of row or an end of row design with active electrical cables or optics or VSR optics going from the GPU host to the tier 0 switch. Very large scale network here. Even larger scale is to replace the spine switches with a chassis that has a higher radix. And the advantage of having a higher radix spine is it lets me build a larger 2-tier network. And staying within 2 tiers, as in this picture, as opposed to going to 3 tiers, is advantageous from a load balancing standpoint, and it's actually advantageous from a number of transceivers standpoint. So I use dramatically fewer transceivers. Effectively every GPU port has 1, 2, 3, 4, 5 transceivers associated with it if this is fully non-blocking, whereas in this network there's 3 transceivers, 1 to the GPU and then 2 in the infrastructure. So we save a lot of money and power on just the optics and transceivers if I stay within 2 tiers. And so we're seeing a lot of customers with a lot of focus trying to stick to 2 tiers in their topology. Even larger scale than that is you can replace the tier 0 switches with chassis that have high radix. I can just build a phenomenally large network this way, and we have customers that are actually doing this as well. We see some, in some cases, some planar, multi-plane networks, in which case the GPU server is, sorry, let me go back. The GPU server is connected to multiple independent planes in some way. Either each NIC is connected to all the planes, or each NIC is connected to one plane. There's different architectures. But this effectively lets me build out a larger scale network and stay within 2 tiers. And so these are planar or rail-based, some people call it. And again, this saves me on optics cost if I can stay within 2 tiers. And that's really the compelling reason to do this. Oops, going the wrong way. This is what it looks like. One of the topologies looks like inside. When I need to cross from one plane to another plane, I do it inside the server because the planes aren't interconnected. And I can do that using the internal scale-up network of the GPU server, or I can do it if my NICs are multi-ported NICs connected to multiple planes. It's the other way to do this. But again, this fundamentally lets me build larger networks in 2 tiers, which saves me on optics cost, saves me on power, better reliability, etc. So the distributed scheduled fabric is something that I talked about before, and I just want to double click on this. This is an architecture, that is similar. We can do a 2-tier architecture today that will scale out to 8,400 gig GPUs or 4,400 gig GPUs. We can do it, again, it's a single logical hop, but it would be tier 0, tier 1, tier 2. We can scale to 32,000 GPUs. This is a lossless fabric between the leaf and the spine. So the fabric is not going to lose traffic. This is 100% Ethernet connectivity to the host, 100% Ethernet, optics between leaf and spine. So use any cabling, any FR4, XDR4, whatever you want between leaf and spine, 100% Ethernet. This looks like a big BGP fabric. It's very familiar to network operators, but we get the kind of data plane performance of a single device. There's no load balancing problems, no congestion internally in the network. It will work well and deliver good performance with any NIC, any transport protocol, demanding workloads, really, really as well as you can do. So this is a very appealing architecture as well. Click on the wrong one. And then of course I can do a multi-planar network out of this to again get to very, very, very large scale as well.
So you're talking about all these really large AI clusters and scales, right? So, I saw in one of your slides, up to 64K server, nodes there. What's reality versus what's theoretical? How many, can you give us an idea? Obviously you can't disclose anything, but we're dealing with 1 or 2 vendors that have 25,000 plus.
Obviously these are, you can go read about what these things cost, and obviously it's not hard to look at these networks and do the math and say that's over $1 billion to build that network. So it is limiting the number of customers that can build networks with 100,000 GPUs. But there have been people out there saying that they are building and have built networks that large. Many, many customers are building smaller networks, don't get me wrong, and those are expensive too. And like just having the ability to, I think from our standpoint, we feel like it's important to have a range of portfolio because people make different choices based on all kinds of considerations.
Right.
And scale down, scale up, being consistent, having one OS across the whole, fleet.
Right.
And different generations might move from, one architecture to the next architecture based on what kind of NIC they have, what kind of workloads they have, whether it's inference or training. There's like all kinds of considerations that the end customers are,
Right.
doing.
But if we drop out of the absolutely absurd, 30, 50,000, are we seeing a lot of AI networking systems and environments that are on the order of a couple thousand, 5,000 types of?
Yeah. I mean, this is always one of these things where like I'm not sure I'm like the person to like completely read the market here, but there's a small number of customers that are building very large systems.
Yep.
And most of the customers are building smaller systems. Like it's not clear where most of the GPUs are going and most of the switches are going, and so like it's kind of there's a small number of customers buy a lot and they have a lot of volume.
So there's also the possibility there's stupid money in some of the AI business right now, and it could be a repeat of like the .com era in 2000, where there were companies that were going out of business with boxes upon boxes of Sun servers.
Yeah, we'll see that. We'll see where that plays out. I mean, like
The dreaded 3-tier architecture that you've got to buy this and this and this.
Yeah, and then never build it.
Yeah.
Right.
And sometimes there would be people that would say, oh, it arrived on the dock, therefore we can count at that as a thing. It was energized, depreciate, amortized. Yeah.
There's one statistic I was reading. There's like the top 10 customers are consuming 85% of the GPUs. Right.
Yeah.
So you can kind of, yes, it is heavily skewed, and you can imagine some of the usual suspects.
Mm-hmm.
Some are public about their cluster sizes.
Plus, too, you've highlighted a lot of features that would frankly be associated with large service providers, not necessarily monolithic single entity concerns. But there's also this notion of that if you get to a size and you are a single enterprise, you're kind of operating as a service provider by default.
Yeah, I mean exactly, and I think the concerns of visibility, load balancing, reliability, power. I mean they play out at the smaller scale as well, and it's just I have less of those problems, but like when it comes up, it's kind of more bad because it impacts a larger fraction of my infrastructure. So people care about it, the same problems. This is a kind of trend that I'll just mention, which is like we talked about a little bit before of just rack scale integration, trying to like integrate more and more GPUs and networking technology into a single rack. And this is really driven by creating larger tensor parallelism domains, more tightly coupled like domains within a single switch, and to enable the ability to use copper optics, which have limited range. And copper optics are really, copper transceivers, are really compelling because, cost is improved, they use less power, and they're just more reliable.
Does this mean cores are now Moores because they're in the middle?
Yeah, exactly. So this is another arc, but it doesn't really fundamentally change any of the network designs. It just makes the leaves look different. So one last thing that I want to talk about is the Ultra Ethernet Consortium, which we have been very involved in. We're one of the kind of founding members of the Ultra Ethernet Consortium. The mission of the Ultra Ethernet Consortium is to advance Ethernet technology to better support HPC and AI. At this point, there's nearly 100 members in the Ultra Ethernet Consortium, like hundreds and hundreds of participants, many companies as part of the Ultra Ethernet Consortium. I mean, this is all on the website. And the Ultra Ethernet Consortium has a whole suite of things it's working on across multiple layers. I don't really have time to talk about it, but this will, and many working groups doing different activities. This is going to result in a specification later this year across many layers, is what we're expecting. We're very involved in it and supportive of it. We're not waiting for the Ultra Ethernet Consortium to show up, and our customers aren't waiting for the UEC to show up in order to build AI networks. We feel like we have good solutions today. It's like more opportunity later, more use cases, more different workloads can be addressed going forward. But like we're very involved in this and tracking it and paying a lot of attention to it and very supportive of it. And all of our switches at this point will be UEC ready.
Back for a second, because it is one specification, and it's not just many layers; it's many features, and you don't need to implement all of those features.
Correct.
You can pick and choose the features that you want out of it. So yes, the spec will be big because you have 100 companies working on it, and some of the companies are working on competing pieces or overlapping pieces or pieces that have nothing to do with each other. And it's,
Correct.
I mean, yes, it's a very huge effort, but ideally, if done properly, it will be a consumable effort because you can pick and choose the features that are important to you.
Yes, and I mean, I think the yes, and I mean, I agree with everything you said. The bulk of the activity is probably in the transport layer in the protocol, which will be invested in the NIC. I just, from my personal standpoint, I feel like the UEC is actually working very well as a team. There's a lot of experience that's gone into the UEC spec. They've gone very fast and very far, and I think it will have impact once it arrives. And there's
for anybody here who's interested, I did write an article about it a month or two ago, and
fantastic.
I can send out a link to it.
Outstanding. So, in summary, I feel like Ethernet is a clear standard for, AI networks. We have a robust silicon roadmap and one OS to cover this. We feel like Ethernet can support the features critical for AI, and there's like many, many network design options from small scale to large scale based on a broad portfolio of platforms to support, many use cases from small customers to large customers with one set of infrastructure.